All right, so in number 8, it says replace the generic constants m and b with their numerical values, including the units. Omit b. Oh, no, that's right. Omit b as 0 if it's close to 0 or logically should be 0. This equation is from your experiment. Which one? Why are they doing this? This was, let's see, maybe numbered differently on yours.
That's kind of why I had those number 8.
Yeah. Number 7 says replace the values of x and y with your v squared. Okay. Somewhere they talk about the slope, the units of the slope. She mentions that. Well, I don't see it on this one, but we're going to do it anyway. All right. So just write this in the space for number 8. So slope. What is slope equal to? Not the number, but just mathematically, what is slope? Yeah, it's y over x. It's rise over run, right? So it's our y values divided by our x values. What are the units on our y value? Our y-axis, what were the units? Meters squared per second squared. What were the units for our x value? Meters. So what are the units for our slope? Meters per second squared. What else has units of meters per second squared? Acceleration. So our slope value that you found is what? Centripetal acceleration. Okay, so that's why I wanted you to put that in there. So just write that in there for number 8. So that's meters per second squared, which is your centripetal acceleration. That's why units are so important, that you know what they are, because they're going to help you interpret what all this stuff means. That number that you got, 30, that I got for mine, 39.56, it's not just a number. It is the centripetal acceleration, because it is in meters per second squared. Okay? So, yeah. So my equation there is your v squared, my 39.56 meters per second squared times r, whatever that r value is. Okay? So that's the main thing that you need to get out of looking at the slope and those units, is that your slope is your centripetal acceleration. And you're going to need that for the remainder of the analysis. This is number 8. So what we're going to do in 9 through the rest of the analysis is we're going to calculate the centripetal acceleration. So we got an actual value, and we're going to calculate what the theoretical value is, and then we are going to look at the percent difference between those two things. Okay, and then you're going to answer questions 16 through 23. Okay, all right, so here we go. Number 9. Number 9, from your free body diagram, you should see that the weight of the hanger provides centripetal force to make the stopper move in a circular path. So the centripetal force is equal to the force of gravity for the hanger. Use this concept of Newton's second law. Write the equation for the motion of the stopper. This equation should include the mass of the stopper, tangential velocity, radius, and the mass of the hanger, and acceleration due to gravity. So centripetal force, Fc, is going to equal to the force of gravity on the hanger mass. Those two things are equal. Otherwise, your thing would have been moving up and down. So what is centripetal force equal to? Formula-wise. Don't give me a number. I want to know the formula because that's what we're doing. We're deriving an equation. What is the formula for centripetal acceleration? Think Newton's second law. According to Newton's second law, a force is always mass times acceleration. Exactly. So we're going to have the mass of our stopper times our centripetal acceleration, because that's the thing that was going in a circle. Okay? And that's going to equal what? What's the other side going to be equal to? Think Newton's second law. The force of gravity on the hanger is equal to what? Formula-wise. What's that equal to? Newton's second law says a force is equal to mass times acceleration. Exactly. But this time the acceleration is what? The acceleration due to gravity. Exactly. Newton's second law is force equals mass times acceleration. And we can put lots of different accelerations in there to look at different forces. If we're talking about the centripetal force, we're going to use centripetal acceleration. If we're talking about the force due to gravity, we're going to use the acceleration due to gravity. That's why it says Fg, little g. So this is going to be the mass of the hanger times acceleration due to gravity. Because remember, in your free body diagram, what was pulling it down? Gravity. Force due to gravity, which is mass. And what are we pulling down? The mass of the hanger, not the mass of the stopper. Okay? So now, what is this equal to? Remember what you just found in number 8. Just found in number 8 that your velocity squared is equal to some number, the slope, times r. What did we say that slope was equal to again when we did that units thing in number 8? Centripetal acceleration. So our tangential velocity squared is equal to the centripetal acceleration times the radius. Solve that equation for centripetal acceleration. Solve for AC. If I solve for AC, what does that equal to? Vt squared divided by r. So centripetal acceleration is Vt squared divided by r. So I can plug that in over here. Because I don't know what the centripetal acceleration should be. I know what it is because of what my linear equation said it was, but I don't know what it should be. Just because I linearized an equation and that's what it said it was, it doesn't mean it's right. Could be off. Why would I be off? Why would that not be true? Why can I not say with 100% certainty that number for slope is the number it's supposed to be? Human error. Did all of y'all have that thing perfectly horizontal all the time? Some of you, I thought you were going to hit your head. It was slanting down kind of low on some of those. So we were making mistakes. It's just, and it's going to happen. It just can't. It is what it is. So we need to be able to find out, like, how far off was I? Okay? That's the point of this. I didn't actually figure out what my theoretical slope should be, or my centripetal acceleration should be. That's why I'm doing this little, we call it a derivation. Just taking equations and with algebra, rearranging them. That's all we're doing. So I can say MS is VT squared over R, MH times G, right? All right. So now, so that gets us through number 9 because we have an equation with the mass of the stopper, the tangential velocity, the radius, the hanger, and gravity. I have all of that in number 9. So this is the final thing you're going to put for number 9. Please make sure you have written in how you got that. Okay? We're not algebra 1 just plugging and chugging. We're making new equations. We're looking at how these things are related and what they actually mean. It's not just a bunch of letters to put in some numbers for. All right, everybody got number 9. Number 10 says rearrange your equation from step 9 to solve for the tangential velocity squared. Okay, so I'm going to give myself some space, and y'all on a paper somewhere, because you need some space, are going to solve that equation from number 9. Solve it for VT squared on your paper by your little lonesome. Solve for VT squared. Okay, what is it equal to? What is VT squared equal to? Just MHG multiplied by R?
No, MHG over meter squared.
That's not meter squared, but the mass of the stopper.
Yeah, mass of the stopper squared.
The mass of the stopper is squared?
No, not mass of the
Okay, okay.
I don't know why I was saying squared, sorry.
That's fine. All right. So we have, let's put parentheses around this. There we go. So we have MGH over MS times R. Does that look vaguely familiar to anything that we have done maybe somewhere around number 7 or 8? Looks like the first one. So what is this part right here? Centripetal acceleration, or the slope, right? So our slope for that equation is mass of the hanger times gravity over mass of the stopper. Remember up in number 8 when I told you to do those units? What did we say the units came out to be? Meters per second squared. Remember, that's meters per second squared. That's kilograms. That's kilograms. So guess what they do? Cancel out. So this is how I'm going to find my theoretical slope, because I know the mass of the hanger, I know the mass of the stopper, and I know what acceleration due to gravity is. So that should tell me what my slope or my centripetal acceleration should have been. So number 11 says, notice this equation is similar to the experimental equation from the graph you wrote in step 8. What does the slope represent? So number 11, you need to answer that question. What does the slope represent? And put what it equals. Mass of the hanger times gravity divided by the mass of the stopper. And then in number 12, you're going to calculate. Using that equation, you're going to calculate your theoretical slope. So go ahead and do 11 and 12. and 13 for that matter, because 13 is just the percent difference. So take what you got in 11, this equation right here, use that to calculate your theoretical slope for number 12, and then calculate percent difference between your theoretical slope and your actual slope that you got from your graph. We're going to look at how far off were we. That right there. Use that, or just that. That's just the slope. No, just the slope is just this part, like you have right here. So what you wrote right there is your answer for number
What
one.
radius is yours?
That's that.
You are, but you're gonna put it into this equation, which doesn't have an arm. So you're gonna take that, put your numbers in, and that's what you're gonna put for number 12. Since we're using the mass of the hanger, the mass of the stopper, and gravity, we should all have the same theoretical slope, the same theoretical acceleration, centrifugal acceleration. You have a minute to get that. The average of the two. You're going to add the two together and divide by two. Oh, no, I'm sorry. That's a lie. We will not all have the same theoretical slope because we all have different stopper sizes. Because yours is 0.375. The number I use is 0.559. So we all have different stopper sizes. So they will not be the same theoretical slope. I was looking at yours thinking, boy, your numbers are a lot different than mine. You will not have the same theoretical slope. Because what's your stopper size? What was the mass of your stopper size? Yeah. That's not there. Or there. So, all right. So for mine, my hanger mass is 0.205. Gravity was 9.8. My stopper mass was 0.0559, which is not all the same numbers for y'all. So I got a theoretical slope of 35.96. Quit doing
I
that.
thought we were really wrong when we had those.
Yeah, no. It's because we all had different masses. Okay. So then if I do my percent difference, That's going to be, for me, that's going to be 39.56 minus 35.96 divided by 37.77 times 100, 9.5%. Okay. My numbers are going to be different from your numbers. This was my actual. This is my actual that I got off the graph. This is my theoretical that I just calculated from the equation in number 11. And this is the average of those two numbers.
Oh, okay.
Percent difference? I think it's over the average. Yeah. Well, there's a percent error and there's a percent difference, and I think they're not the same thing. I think what you're determining is the percent error, and I want the percent difference, and I don't think they're the same thing. So percent difference over here was subtract them and divide by the average. So we're going to, in here, it's going to be the same thing. Subtract them and divide by the average.
Oh, so
Percent error, like you do in chemistry, that is actual minus theoretical divided by actual, but that's not what we're doing. We're doing percent difference. Okay. So your actual comes from the graph. Your theoretical comes from your equation in number 12. And then you average the two together.
I just remember that. I think that's
Yeah.
what I was getting mixed up with.
Yeah, there is a percent error and there is a percent difference, and I do not think they're the same thing.
I hated that.
Percent error?
It's so confusing.
It's so easy. You just, if you know the formula, it's easy. Just plug in numbers in.
Oh, but that's all percents on both of them. They're both the same thing.
Yeah.
But then there's like difference in error. I'm like,
Mhm.
whoa, that's probably why I was getting it wrong.
Yes. You have to make sure you read the whole thing. All right, so on 15, it just asks you, so 14 says to take all the answers from step 6 through 13 and put them in the data table. So to fill in the last 3 rows of that data table, you've already put in your slope, you've already put in your y-intercept, put that in from the graph. But it asks you for the rest of those numbers, it asks you for the equation, the theoretical slope, and the percent difference. That is all going to come from questions 6 through 13. And so again, everybody's is going to be different since we all had different stopper masses. I really like that. So take the answers that you just worked through and just write them in the table here, here, and here. So we already filled those out from our graph. Now we're just going to fill these in. Okay. And those just come from your questions. That's it. Okay. All right. So fill those in for a second.
I got a question about the
Yeah.
percent difference on that
Mhm.
same thing. Are we finding the percent difference between the measured force and the actual force? That we're doing?
Yes, that is what you are doing.
So we just,
So-
find the average and then-
Right. You're going to take the difference between these two, then you're going to take the average of them and divide the difference between them by the average, then multiply by 100.
If it goes over the actual average, then,
What do you mean?
like, so our actual average is 2.01 and we go to 2.2.
That's fine. Yeah, it's fine. You're just going to subtract the two and divide by the average. Yeah. So don't forget to fill in your percent difference on this column too. All right, so let's take a look at the questions. Let's take a look at these questions. Now relate the mass of the International Space Station to the mass of the stopper. What will happen to the orbit of the station around the Earth as it grows due to construction? How can you correct the orbit without losing mass? So you need to be thinking about how did mass affect your numbers. Are these the same question? I don't think these are the same questions. Hang on. 15? Yeah, you have to do number 15. Describe how adjustments in the stopper's mass would affect the velocity. Use algebra to justify your answer. So, do 15 first. Okay, so your elaborate questions are a little different than mine, I believe. Let me see. Hey, let's see your. Oh, okay. All right, so what happens? So what was your answer for number 15? What happens if you increase the mass, the stopper mass? It decreases the tangential velocity. And so, yeah. So if you look at step 10, the mass of the stopper is in the denominator. And since the mass of the stopper is in the denominator, right here, if we increase that mass, that means the whole thing is going to decrease. Okay? I was noticing on your quiz, a lot of people didn't get that question right because we forgot the algebra part of it. Okay? So, what you need to do is work on questions 16 through work on questions 16, 17, and 18. And then we will look at 20 together in class tomorrow. Well, you know what I mean. Monday. Don't forget to be working on your practice problems for 9.3 and 9.4. Getting those ed puzzles caught up, and we'll start putting in zeros if they're not done. So make sure you get those done. Yeah, we'll need to do them next week. Do you have a study hall or something like that?
I don't have study hall.
Okay.
I have a third grade computer class.
Can you come in early one day?
Yeah, I come early.
Yeah, pick a day next week when you can come in early, and I'll let you do it then.
I don't retake the grade. Now I'm mad at myself for confusing percent difference.
Just don't confuse them anymore.